Hello everyone, welcome to this presentation on concurrency control and of the advanced database course. Let's dive deeper into some concurrency control techniques that ensure smooth concurrent operations in databases. So this is the brief overview of the topics that we will be covering. We will be covering multiple granularity. Next we will be going for weak levels of consistency. Then we will be going for snapshot isolation. So let's start with multiple granularity. So what is multiple granularity? It refers to the locking data items at various levels of a hierarchy, helping balance performance with data consistency. It's useful when managing complex data systems and can be visualized as a tree. Hence, transactions can either lock a node explicitly or implicitly lock all its descendants. We can use two types of granularities, which are fine granularity, that is lower in the tree, which results in higher concurrency but higher overhead of managing the locks, and coarse granularity, which is higher in the level of the tree but it results in lower concurrency and but it has less overhead. Then we also have a concept of intention locking. Now, let's imagine a scenario. Suppose down the tree, a transaction T1 locks a data item R1 in exclusive mode X. It would mean that the descendants of R1, let's say R11 and R12, would also be locked in exclusive mode. Now, suppose that another transaction wants to lock R11 in shared mode. Should it be allowed? Let's see. So, in intention locking, we have five modes, that is the shared lock, exclusive lock, intention shared lock, intention exclusive lock, shared and intention exclusive lock. So, let's discuss the three new locks that we have encountered, namely the IS, IX, and the SIX locks. So, intention shared lock, it indicates explicit locking at a lower level in a tree but only with shared locks. That means if I have a tree, let's say this tree, here in the database, if I lock R12, the data item R12 in exclusive mode or shared mode, then it means that the R1, A1 and the database would be locked in intention shared lock, which means that there is a locking in shared mode in the lower level in the hierarchy. Next is the intention exclusive lock. It indicates that there is a locking at lower level in the tree, explicit locking, which is exclusive or shared lock. It is generally used for exclusive lock and not for shared lock, because for shared lock we have a separate lock, that is the intention shared lock. So let's say in this tree we have there is a transaction which locks R31 in exclusive mode. Hence R3, A2 and the database would be locked in intention exclusive lock. Next is the shared and intention exclusive, which means that the subtree rooted by that node is locked explicitly in shared mode by transaction and there is explicit locking at a lower level. Which means that, for example, if I want to read the data items in R4, I would lock it in shared mode. But also, if the same transaction wants to update R41, then that would be locked in the intention in the exclusive mode, which means that R4 would be locked in the SIX mode. So now let's look at the compatibility matrix. So this is the compatibility matrix. So if a node in the tree has intention shared lock, then it can be concurrently locked in intention shared, intention exclusive, shared and SIX mode, but it cannot be locked in exclusive mode. If it has a intention exclusive lock, then it can only be locked in intention shared or intention exclusive lock and not in the other three. If it is holding a shared lock, if the node is in shared lock, it means that it can only be locked in intention shared or shared mode. If the node has a SIX lock, then it can be only locked in intention shared mode, and if it is holding an exclusive lock, it cannot be locked in any other mode until the transaction which is holding the exclusive lock releases that lock. Now this is the compatibility matrix. Let's see the locking rules. So there are specific rules that we always compatibility matrix must always be followed. The always we start locking from the root node and we respect the 2PL protocol. That is, each and every transaction which is following this locking scheme must follow the two-phase locking scheme. Two-phase locking is that if a transaction is obtaining locks, it can only obtain locks, and once it releases any lock, it will release all the locks. It cannot gain any lock after releasing any locks. So that is the two-phase locking, which consists of two phases. That is the locking phase and the unlocking phase. And node can only be unlocked after all its children are unlocked. Else it cannot be unlocked by the transaction T. So this is the example which we used in the explanation. Now let's go for weak levels of consistency. There are times when we want that strict consistency is not needed. For example, if there are concurrent updates in the Amazon's orders currently going on, and let's say Jeff Bezos is sitting with the team and wants to see some statistics regarding the daily orders. So it doesn't matter if one or two orders which are in process at that time are calculated in the total or of the balance or not calculated, because one or two orders would hardly make any difference. Hence, it does not matter. So in that cases, we can go for weak levels of consistency to increase the performance. So that means there is a trade-off between accuracy and performance. Such transaction may not be serializable as well. So there are four types of levels of serializability, levels of consistency in SQL 92 defined standard. So they are the serializable, which is the default type. It ensures full consistency. Each and every transaction, before the transaction, during the transaction, after the transaction, the database will be consistent as long as it does not fail in. Then is the repeatable read. It reads only committed records. Repeated reads will return the same value. However, that might not be serializable, because let's say there are some transactions which are not yet committed and they have made changes. So those will not be serialized since those changes will not be there. Next is the read committed. That only committed records are read, but successive reads might give different values. That means if I perform a read on the any column of the table, and then some other transaction updates the table, and then I perform the read again, the values might be different, since that particular transaction which occurred after my first read might have updated some value in the column. And next is the read uncommitted. Even all the uncommitted reads are also read, which is not at all serializable, and not it is not even preferred. Next we'll see snapshot isolation, which is a type of level of consistency supported by Oracle, but it is not the part of SQL 92. So let's have a look at snapshot isolation. What is snapshot isolation? So snapshot isolation is a concurrency control mechanism that each transaction operates on a consistent snapshot of the database taken at the start of transaction. So let's say there are two transactions which are concurrent. So each transaction at the starting clicks a snapshot of the database at that state and operates on that snapshot itself. That means that the global database, which is the main database, is not affected until and unless the transaction is committed or aborted or is, let's say, completed. Hence, the transactions which are concurrent do not see changes made by others during their execution. So, in this case, we generally follow the first committer wins rule. That is, under SI, the first committer win rules applies. If two concurrent transactions or more transactions try to write to the same data item, the one that commit first wins, and other transactions are rolled back. That means that if, let's say, I have a transaction which says that increase the balance by 50 rupees, and other transaction decreases the balance by 100 rupees. So if the transaction which decreases the balance by 100 rupees commits first, then the transaction which is increasing the balance by 50 rupees would have to be rolled back, since the first committer rule is applied and the second transaction is already committed. Then we see at the snapshot read. The changes made by concurrent transactions are not visible to the transactions until they are committed. Which means, let's have a look at the example. Let's say we have two transactions which deducts $20 from A and T2 adds $20 to B. So when the T1 first reads the balances A and B, which is 100 and 0 respectively, T2 also reads. Then T2 writes B as 20, and then if, let's say, T1 writes A as 80, that is deducts 20, and then reads B. So it will still read the value of B as 0 since T2 has not yet committed. If T2 would have committed, then it would have read the value as 20. But it is not the case. Similarly, in T2, if it reads A, it will still read 100 and not 80. So next let's have a look at the snapshot write. So let's say we have two transactions as in the last slide, and let's say transaction T1 commits first. So transaction T2 would be rolled back since the first committer rule is wins rule is applied. There is also a variant which says that the first updater wins, which states that the transaction which first updates would win. In that case, transaction T2 updates first, that writes A to 20 and commits later, but it has updated first. So that would be win and transaction T1 would be rolled back. So what are the next? Let's have a look at some benefits of snapshot isolation. So here are some benefits that reads are never blocked in snapshot isolation. Also, other transaction activities are also not blocked. Only the writing is blocked or even rolled back. Hence, it avoids dirty reads, lost updates, and non-repeatable reads. It ensures consistent behavior for predicate-based queries, but it might not guarantee consistency in everything. So let's see where. Integrity constraints might be violated since those checks are generally done before the snapshot is taken and after the snapshot has been updated, and that is the transaction has been completed. Snapshot isolation may also lead to phantom phenomena, which means that transactions might be conflicting on non-common data items. Let's say there is a transaction T1 which deletes a data item T1 and other transaction T2 which reads the whole table and calculates the sum. So in that case, transaction T1 might delete the transaction and T2 would calculate the sum which includes that transaction because the snapshot would be the same before the deletion. Hence that might lead to a problem because that particular data item, let's say R1, would no longer be in the table and hence the result would be inconsistent. So these are the problems with snapshot isolation. So that's it from my side, and thank you very much for listening.